Okay, in this next set of videos we're going to extend our discussion of time value of money, that topic, and we're going to look at, instead of lump sums that we've dealt with in the first set of videos, we're going to consider a second type of cash flows, and that is a series of even cash flows. So no longer just one cash flow, a lump sum at some point in time, but we're going to consider a series of cash flows, so several cash flows that are equal, so they're even cash flows, and they're occurring throughout the timeline. So first we have this definition of an annuity we need to consider, and our working definition for an annuity will be a series of equal cash flows that occur at equal intervals for a set period of time. So for instance, we have a mortgage, and mortgages are due monthly. If it's a fixed rate mortgage, which is what many of them are, then we have a fixed interest rate and therefore a fixed payment. So it starts to fit our definition of an annuity. And it's going to happen over a set period of time. So over a 30-year period, if you have that kind of mortgage, that's the annuity of the mortgage. Now there are two types of annuities, and they're differentiated by when the cash flows occur, the timing of the cash flows. So an ordinary annuity, and this is what we'll be dealing with for most of our problems, most of our questions. An ordinary annuity is when the cash flows occur at the end of the period. An annuity due is an annuity where the cash flows occur at the beginning of the period, and that has some implications for the value of those annuities, and we'll look at that here in a few minutes. So with our series of cash flows, we can solve for all the same things that we did in calculations for lump sum payments. We can solve for the present value. We can find out what the value is today of all these cash flows that we're regularly receiving in the future. We could also solve for the future value of an annuity. So we're answering the question then, how much will all these regular cash flows be worth at some point in the future? And we can solve for the number of periods, we can solve for the interest rate, and we can solve for the payment itself, so the amount of the regularly occurring payment. So we'll look at examples of each of these in turn as we go through this video. Now, we're not going to derive any of the formulas for annuities. I'm just going to go ahead and give it to you, but we're going to stick closely to Excel. We're going to use Excel to do our calculations. We can do a lot more stuff in Excel. It's much more powerful. We can answer much more interesting questions that are related to time value if we start to move away from the formulas. But just to show that it works, let's look at this ordinary annuity formula. On the left hand side, we've got the future value of the annuity denoted by the FV with a sub A. It's equal to the payment amount times, and then this ugly thing in the brackets, 1 plus the interest rate raised to the nth power divided by the interest rate. And then from that we're going to subtract 1 over R. So once we get that piece done within the brackets, we're going to multiply that times the payment, and that gives us the future value of the annuity. As a calculation here, let's start to plug in some of the pieces for a $3,000 annuity, and it's going to be an 18-year annuity with a 7% interest rate. So the R is 7%, the N is 18, and the payment's $3,000. So we can just plug that into the formula, and we will get an answer of $101,997.10. It's quite cumbersome to do that in a calculator, to stick in all those pieces and make sure you keep everything straight, your order of operations and the parentheses and everything else. Thankfully, Excel excels at these kind of calculations, and so we can go there for the work. The formula for an annuity due, recall that an annuity due is a series of even cash flows that occur at the beginning of a period. So anytime we have an annuity due, what we actually have is an extra period of compounding. And so to get the amount of an annuity due, what we're going to do is take the future value of an ordinary annuity and then compound that one extra period. So we're going to multiply that times 1 plus the interest rate. So in the previous example, if we had invested $3,000 at the start of every year for 18 years, and earned the 7%, we would end up with $109,000 instead of the $101,000, $101,997. We'd have an extra year of compounding, so our amount would be bigger. All right, let's look at calculating the future value of annuities with Excel. Again, we're going to use the FV function, so we'll put equals FV and then the things in parentheses. But when we're talking about a series of even payments, now we finally have something to put into that payment portion of the Excel function, the payment argument. So in doing Excel calculations going forward, I'm going to show you a framework that makes it nice and easy. It's a good way for you to show your work to me on quizzes, tests, etc. It's a nice way to keep everything straight, and it's also helpful in kind of replicating calculations, doing things over and over where you might just change one of the inputs. In Excel, what I'm going to show you is we'll set up the spreadsheet to have 5 possible inputs: the present value, the future value, the number of periods, the periodic interest rate, and the payment. And what we'll do is just solve for the desired output. So in this case, we're solving for the future value of an annuity. So let's go to Excel and look at some annuities and find the future value of them. So the first example here, what is the future value of $3,000 invested for 18 years at 7%? So this is the exact same question we had in our slide a minute ago. We have the 5 possible inputs here: the present value, the future value, the number of periods, the interest rate, the periodic interest rate, and the payment amount. So let's put in the inputs, the arguments for my future value formula over here on the left side. It's kind of like the givens in the equation. The present value is 0. We're starting with 0. We're going to solve for the future value, so I'm leaving that blank here, and actually we'll do the calculation over here to the right to kind of set it apart and highlight the work that we're doing. The number of periods is going to be 18. The periodic interest rate is 7, and the payment amount is going to be $3,000. I've made that a negative because we're investing that money. We're sending it out to our investment company, to the bank, to whatever. So we're going to have a negative cash flow there, and the result is we're going to have a nice big positive cash flow in the future. So this confirms our answer earlier that after 18 years of investing $3,000 at the end of each year, by the way, this is an ordinary annuity, we'll end up with $101,997. Okay, let's just real quickly show what happens with an annuity due. We have those exact same inputs, the 0, 18 for N, 7%, and then negative 3,000. But in our formula, in the function, the future value formula here, we've got FV, and we have the rate input. And notice now I'm starting to use Excel in a more powerful way, where I'm referencing cells with my inputs, and I'm leaving my formula, my function here, linked to cells. And this can kind of leverage the capabilities in Excel where I can come up with a series of answers by just changing any one of those inputs instead of retyping the whole formula like we have been, where I might type in equals FV, comma, 0.07, comma, 18, comma, etc., etc. I can now refer to cells, and it makes things much better. Back to the Excel function here, we have the rate input, the number of periods input. The number of periods is shown in cell B12. We have the payment amount, that's down at the bottom, B14, the negative 3,000. We have the present value, that's cell B10. And then the very last thing here, notice that it says type. And by the way, the type is set in brackets, and that is an indication that this is an optional input in Excel. You don't have to put something there. The default is a 0 or nothing, and the default is an ordinary annuity. This 1 is an indicator that says this annuity is an annuity due, and it tells Excel to change how the calculations are working. So by sticking a 1 there, we're telling Excel that this is annuity due. Notice that up here in the calculation we did earlier, there is no 1. There's nothing there. I could put a comma and a 0, and that very explicitly says that, look here, the payments are occurring at the end of the period. If I put a comma and a 0, it doesn't change the output at all. So that is a ordinary annuity, and by sticking a 1 at the end, we've got an annuity due. So the answer, again, we saw this in a previous slide. The answer is $109,136. And let's look at a couple more before we end this video. How much money will I have in 40 years? So this is a future value thing. If I save $1,800 per year, so we have a constant amount of $1,800, we have a constant period of a year, so we've got an annuity here. And the interest rate, it's earning 8.5% per year. So we've got our 4 inputs here. I've got a negative in front of the 1,800 because it's an amount we're investing. And then I solve over here by using the future value function. B23 is my rate, that's cell B23. The number of periods is in B22, etc., etc. I didn't stick anything in the type because this is an ordinary annuity. That will be our default to have an ordinary annuity. And the result is, shown here in this yellow cell, $532,228. So that's what the future value of that annuity would be if I'm investing it. If I'm investing $1,800 every year and it's earning 8.5% all along the way. As an aside, let's just real quickly look at this other calculation here as a precursor to the next video. I'm going to ask a question here. How much could you buy in 40 years with that money we just calculated? So in 40 years, if I save $1,800 per year, I'm going to end up with $532,000. How much can I buy with that $500,000? What's the purchasing power going to be? Let's assume that inflation is going to be 3.3% per year for the next 40 years. So how much money will I really have? Now, if we start sticking this into our calculation framework again, now we have a future value, right? We just solved for it. So that number is 532,000. And notice that I referenced my answer up above. That's always a nice thing to do in Excel, is to link your cells so calculations kind of flow through the whole spreadsheet. So my future value is 532,000. The number of periods we're talking about is 40. Now my interest rate is 3.3%. That's the inflation rate, but that's the percentage that I'm going to use. Now there's no interim payments. All right, there's no regularly occurring investments along the way. I'm just asking the question, this lump sum, if I had a lump sum in 40 years of $532,000, and those dollars, by the way, are worth less than they are now because of inflation, how much is it really worth in today's money? And the answer is $145,239. The purchasing power of my $500,000 40 years from now, I would really only be able to buy stuff that's worth $145,000 in today's money. So that's just a brief aside. We'll pick up with some more present value calculations of annuities in the next video, and I'll see you then.